Chapter 5, and you may be wondering, why do electrons get their own chapter? Well, it's because when you walk up to an atom, the first thing you encounter, we just learned the electrons are flying around the atom. So electrons are the first thing you will encounter. Because of that, they will determine the reactivity of an atom. So if the nucleus in this picture were the palace, then the electrons are the first things you come up to, and right, it's the first impression. Are they smiling? Are they angry? Are they looking for war? And that's going to be true with atoms. Different elements will have a personality based on the electrons that you encounter as you walk up to it. So that's why electrons are important. They're the outermost thing of an atom and thus determine the reactivity. And as an example of that, we have John Travoltage here. So let's play with John Travoltage a little. Let's, shall we? So electrons, because they're on the outside, they're the things that move. Okay, and the reason why you have static electricity and electricity in general is the electrons moving around. So moving your foot on a rug brings all the electrons into your body, and then your body can then move those electrons to the doorknob when it does that. Okay, and again, like I was talking about, so helium, neon, argon, krypton, these have similar properties because of their outermost electrons. Fluorine, chlorine, bromine, iodine have similar properties because of their outermost electron. Oxygen, sulfur, selenium. That is how that works. So that's why electrons are important. As you can see here, when you have a long wavelength, these things aren't quite as scary. And when you have a high wavelength, right, shorter wavelength, these things start getting scary, right? X-rays, gamma rays, ultraviolet. These are things that are in the news for causing cancer, and you wear the lead thing when you go to the dentist and makes the Hulk. Whereas the things down here, radio waves are in the room right now, and microwaves are how phones work, so those aren't. And then in between these two, we have visible light. Okay, so let's talk about sort of the breakdown of a wave. A wave has a wavelength, and a wavelength is sort of the point of one wave to the same point on the next wave. So one way to do it is from crest to crest, from the top of one wave to the top of another wave. You can do it from bottom to bottom. Often, unfortunately, in chemistry, we start here and we go up, down, and then when we're coming back up again, and it ends here. So that's considered one wavelength, sort of this Z-shaped thing that's on the side. That's what we consider one wavelength. So we give the symbol lambda as the wavelength symbol because we have to, hats off to the Greeks, and it's a distance from one point to the same point on the next wave. And then the frequency is how many waves you make per second. All right, and we gave that the symbol nu, which looks like a V, basically. Okay, so in your life, you've heard of some constants, right? There's pi, there's the speed of light is a constant. You may not have known that, but it's true. And there's also something called Planck's constant, and it's not related to Plancking, the phenomenon that is here being demonstrated by a basketball player who plays with the Lakers. And he's really old, and he used to be with the Orlando Magic, and I can't think of his name right now. Anyway, you know who I'm talking about. Guy who's with the Lakers, used to be with the Orlando Magic. Dwight Howard. Dwight Howard? Dwight Howard. Yeah, okay. So, a constant can be limiting. In this egg, right, at Easter time or springtime, you get these eggs that are filled with candy. It turns out I can only hold 48 M&Ms in that egg. I counted. I put them all in that egg, and you can shake it all you want, and there's no room for anything to shake if you put 48 M&Ms in there. So I can have all those M&Ms be the same color. If I want two colors, though, in order for 48 M&Ms to fit in there, I have to start taking some of the green ones out. So to take some green ones out to make room for red, two colors now requires fewer M&Ms of each kind, right? Less M&Ms of each kind. If I want to put three colors in there, same thing. I now have to take out more of the red and the green so the blue can fit. If I want to put four colors in there, I need to take out some of the red, green, and blue so that the yellow will fit. Because of this constant, because of the fact that it only holds 48, I can't just add yellow to what I had in this situation, right? Here's a situation that I can't just add yellow to because there's not enough room. I have to take some out to make room for the yellow. So keep going. I can add 6 colors by pulling more out. I can add 7 colors by pulling some out. So basically what we're learning is that's the way the constant is limiting these M&Ms. The M&Ms have to equal 48. So if I want to put some more colors in, I have to take some of the actual M&Ms out. And that would be graphed like this. So if I have the number of colors in blue, I can increase my number of colors. Look at this. I mean, they're going to do blue, right? So my number of colors increases, but at the same time, my number of M&Ms of that color will go down, right? So this is going down while the other one's going up. So the more colors I add, the fewer of each kind of color I have to have. And that's because of that constant. We have that constant at 48. So because of that, these things have to equal when you multiply them 48, right? 2 times 24, 3 times 16, 4 times 12, 6 times 8, they all equal 48. But as one goes up, the other one has to go down to make up for the fact that you're putting more stuff in there. We call that an inverse relationship, one increasing and the other decreases. Turns out, I went through all that M&M talk to discuss the fact that the speed of light being constant, 3 times 10 to the 8th meters per second, always equals the wavelength times the frequency. So you can't have both a high frequency and a long wavelength because they have to equal that speed of light. So if one goes up, the other one has to go down. So if the speed of light, if the wavelength is going up, the frequency has to go down. If the wavelength is going down, the frequency has to go up. Let's do that. So if this one's going down, then this one has to go up. Okay? So that's what you see here. A high frequency, a lot of waves happening in a short amount of time means the wavelength has to be short to account for how often you have to have those waves happening. If you want to have a long wavelength, then the frequency has to go smaller because a long wavelength can't happen as frequently as a short wavelength. And that's an inverse relationship. So with energy, though, this actually goes the other way. Energy equals Planck's constant times the frequency. So therefore, they have a direct relationship. One goes up and the other one goes up. So energy and frequency, because the constant now is on this side of things, as one goes up, the other one goes up. So higher frequency means more energy. So going back to this, that's what we were discussing with, right? These have high frequencies. The short wavelengths, so very high frequencies, they're going to be like this. That's why they have so much energy. These have low frequencies because they have long wavelengths, so they're going to be low energy. There's another one. This is the one I give you on your tests and stuff, or recommend for you to use, but this one, because it has to be printed in color, you might not understand it. So you can use this one if you want, but you can't print it in color. Well, you can print it in color. We might have also around. All right. So let's do some problems, shall we? So the equation is that the speed of light is equal to the wavelength times the frequency. So I'll make wavelength red and I'll make frequency blue. So in this first question, it says, what region of the spectrum, if we excite atoms of xenon and they emit radiation at 4.0 times 10 to the minus 7, what area of the spectrum are those in? So 4.0 times 10 to the minus 7, you'll see here will fall in this region here between 4.2 and 4.0. So therefore, times 10 to the minus 7, right? So therefore, they're going to be violet in color. So 10 to the minus 7 is up here, right? So it's on the verge of ultraviolet, but since it's in the visible light region here, we are going to say that those are violet. All right, so visible is what they fall in. And then what frequency does this light have? So now it's looking for the frequency. We know the wavelength, so we know this, right? So 4.10 times 10 to the minus 7 times that frequency is going to equal the speed of light, and the speed of light is a constant for all light, so it's 3 times 10 to the 8th meters per second. Okay, so that's our equation. We're looking for this x, so we're going to divide both sides by the 4 times 10 to the minus 7. So we divide both sides by 4.10 times 10 to the minus 7, and that'll give us our answer. All right, so 0.10 e -7. All right, so that's 7.32 times 10 to the 14th. So our answer becomes V equals 7.32 times 10 to the 14th. And the units of frequency are called hertz, which means waves per second. All right, let's try another one. So in this one, I'm giving you the frequency. So now you have this. And we have to find the wavelength. So we're looking for the red one. All right, so same thing. Speed of light is the constant. It's the same no matter what. So 3 times 10 to the 8th. You might want to write that down in your notes as something to remember when you're taking these quizzes and whatnot. That's going to equal whatever the wavelength is, which I have to find out, times the frequency, which is 4.76 times 10 to the 16th. Now I want to do this one. You need to know how to use your calculator. So here's how I'm going to put this in the calculator. This will go in as 3. I use the E button. Now, unfortunately, even though it's an E button, on many calculators, it's an EE button. So you'll have to figure that out. This is where it was better to be in person. But anyway, so I'll hit 3E8. So what that means is 3 times 10 to the 8th. And then I want to divide it by, so I'll hit the divided by, and then same thing here. In my calculator, I will put in 4.76. In my calculator's case, it's an EE, and I'll put 16. If that were a negative 16, I would have to put a negative here, and you would use the plus minus button if it were negative, not the plus button meaning adding or the minus button meaning subtracting. You want to use this plus minus button, and you get this number, which if I put into scientific engineering is 6.30 times 10 to the minus 9. So the answer you should get from that is 6.30 times 10 to the minus 9. Okay, so let's think about this for a minute here. If we're trying to figure out what kind of light has a frequency of this, if you go back and look at the thing I gave you, which of course is not right here. Okay, so this is the thing I gave you. These are all measurement in meters. These are all wavelengths. So I can't tell what kind of light it is if someone tells me the frequency. I have to do the little math that we just figured out. So let's do the little math. And again, we'll do it. So we're going to use this equation that the speed of light is equal to the frequency times the wavelength, right? And in this case, we have a frequency. So we know the speed of light is 3 times 10 to the 8th. And we know that the frequency is 8.5 times 10 to the 12th, 8.50 times 10 to the 12th. So now I'm trying to find what my wavelength is. This is my x. So I'm going to divide both sides. So I'm going to divide 3 times 10 to the 8th, right? Divided by 8.5. So now let's talk about the other way you can do this on your calculator, which is often embraced because nobody can really find the E. So if I'm going to put this into my calculator, I can do this. I can say 3, whoops. Let's erase that. Okay. Going again. Here we go. So if I want to put that in my calculator, I would put 3, and then you can say times 10 caret 8, right? That means 3 times 10 to the 8th power. Then you're going to hit divided by, and now, because of all this, and you like using this method, you have to put parentheses. So please, whenever you do something in the denominator, it has to be in parentheses, because otherwise it's going to take the times 10 to the and put it in the numerator. So parentheses 8.50 times 10 caret 12, and then close parentheses. So if you do it that way, it'll work without the e's. That's fine. And then But the key here is if you're not using E, you have to use parentheses. And that's a choice you can make. That's fine. A lot of people can find that. But you should be getting your answer on something like this as 3.52 times 10 to the minus 5. So if you didn't put that in parentheses, you would get 3.52 times 10 to like the 20th power. And that is not times 10 to the minus 5. This is wavelength, which is length, meters, right? So this answer is in meters, okay? If I ask you for your frequency, your answer is going to be in hertz. Okay, so contact me if you want to play with the calculator some, because that is something I prefer to do almost individually. But if you're having problems with that, let me know. Okay, electrons are responsible for atoms absorbing and releasing light energy. The wavelength of light is inversely related to the frequency, and that the energy is directly related to the frequency. This is what we know so far. Bohr figured out this wonderful thing that if you take hydrogen gas and you excite it, so you put electricity through it, you get, instead of what he was expecting, sort of like a spectrum, right? Anytime you see light through a prism, you see sort of that pretty spectrum. And what he saw instead was parts of the spectrum, but very specific lines. Okay, so let's take a look at that. So that was interesting to him, because why isn't he seeing all the colors? He's just seeing these very distinct bright lines and nothing else when he looked at it through his prism. So law of conservation of energy, right? Energy cannot be created or destroyed. It changes forms. So what he came up with was that these electrons must be jumping around from one set place to another set place. And because these places are so established and set, that's why he's seeing the specific light and not all the light. And there's a little video of me jumping up and down a hill to explain this further. But basically, he came up with this idea of these energy regions, because if an electron is going to get light energy, it will go up to another level. And then when it comes back down, it's going to release the same energy that got put into it. Okay, so again, take a look at my other little video, me jumping up and down. Because of this, we have these nice emission spectra. And the only reason I bring this up, this is more to interest you. This is how we know stars have certain atoms on it, okay? So when we look at our sun, you see how these each element sort of has a very distinct fingerprint, right? Neon doesn't look anything like helium. Helium looks similar, but not exactly like hydrogen. So if you were to look at something like a sun that was emitting these things, you could tell what atoms are on there. So when we look at our sun, what we see is hydrogen and helium. Turns out the sun creates all the elements, all suns. So our sun is pretty young because it's only gotten to hydrogen and helium. An older sun would make all the elements. So if we were seeing bromine on our sun, we know it's gone through quite a while to get to bromine. So all the elements basically come from these stars in the universe, and as they get older and older, they make more and more and more elements in order. So one happened, two happened, and think about what we just learned, right? It took a proton to make a hydrogen, took a proton, two protons with some neutrons to make helium. It's going to take three protons with some neutrons to make lithium, four protons, right? So after it makes one, the sun, having all that energy that it has, can just keep smashing in a proton and make the next element up. So as that happens, and then when a sun supernovas, it releases those elements into the universe. So that's interesting, right? That's why we did that. So because of that, Bohr came up with the idea that there are these areas of electrons, and that the first one being so close to the nucleus, it can only hold two, and the second one being further from the nucleus can hold 8, and then the third one being even further can hold 18, right? Because the rings are getting bigger, they can hold more electrons. So this is what we call a Bohr diagram, where he has this sort of image of things going in orbits around the nucleus. Now we know this isn't actually true. What um, One of the problems with Bohr's model, he was actually trying to do some calculations along with it. The calculations only worked for hydrogen. Once you did anything else, helium, lithium, it didn't work anymore. So he was able to predict these things, and that's why we have what's now called the quantum mechanical model. So it's similar. It's not the orbit he was saying, it's more of a fuzzy probability area where you'll find electrons. Um, so it's very similar. If you understand atoms as Bohr, you can probably get through a lot of programs. But the reality is, it's a little more of a fuzziness that you're just more likely to find electrons in certain areas and you're less likely to find them in other areas. And at the end of the day, they kind of look like rings, but it's not an exact orbit. It's much more random flying around.